So, last time we talked about angular velocity, and this time we're going to talk about angular momentum. But first, let's actually talk about angular velocity, and what it means, like in unity. So, if you remember, we found that a centripetal force is equal to minus mr omega squared times this direction, and this direction again is the tangential velocity. It's the velocity, like it's like the orbital velocity. It's the orbit when you it's the velocity going round the circle, right? And then we have this direction, right, which is our r hat, which shows how close we are to the center, right? This shows how our angle changes. Okay, so there's our angle, right? So we also know that this thing is equal to this, right? And the direction happens to be there, right? So it's a force that pulls you in, right? Or maybe that's not there. Maybe that direction is wrong, because the force definitely should be inwards, shouldn't it? So I think actually... Oh, yeah, remember. It was definitely R, wasn't it? Because we had RR, and that equals R. Okay, so never mind that. But, yeah, it's always going inwards, right? This direction is always going inwards. So, we can call this a centripetal force, and it's a force that pulls you in. And really, you're only ever gonna encounter 3 of these. One we're not really interested in. One is gravity, right? Right. The second one is like a rope or any kind of tension, kx, right? And the third one is going to be qq over 4 pi epsilon naught r squared, which, you know, we don't really use because we don't really care about electrons and stuff like that. Because in our real world, we don't really interact with electrons, right? We only interact with them insofar as they move through a wire, or occasionally if you get struck by lightning and you're very unfortunate, then that will happen. But in general, we almost never do this. But you know, if you want to learn electromagnetism, then this is Coulomb's law, and you can go, you know, look that up and learn how to use it. It's just positive charge, negative charge. We don't really have to worry about it. The main thing is we can say, well, okay, these forces can always act on you. For instance, if we have just something that's drifting through space and it has no velocity right now, right? It happens to be at rest in our frame, and we see it being pulled towards the Earth. Well, it's just going to get pulled in, right? There's nothing stopping it. It's just going to fall in, and it's going to get crunched into the center of whatever's pulling it. Okay? But the difference is, if we add a velocity to this thing, so if this is already moving, then it'll start to orbit. So if it's got a low velocity, it's going to go like, it's going to shoot round like this, right? If it's got a high velocity, then it's going to shoot round like that. Okay? But if it goes around in a perfect circle, that is going to be a centripetal force. So we can find out what velocity to give this to make it centripetal. So if we put mv squared over r equal to these things, right? So let's start a new slide. If we do mv squared over r equals gmm over r squared, right? Direction we're not bothered about right now. We're just worried about magnitude. So these are not vectors, okay? And, you know, these have minuses, but they're both minus, so it doesn't matter. Well, we can cancel one of them, cancel that, and we end up with v is root gm over r, right? And the velocity is going to be in the tangential direction, right? It's going to be that way, right? It's going to be going, if we have something orbiting, or I mean, it could be going the other way. It could be going, you know, that way. It doesn't really matter. It will still it will still be centripetal as long as, you know, it's going at some kind of velocity. Well, the force will always keep it in, you know, it will keep it moving centripetally. Because, you know, you might look at this from the other side. We might see it going this way, but someone who's all the way over there in the Z direction, someone who's like over there, they're going to see this moving the other way around, right? It's going to be here for them moving that way. So it doesn't really matter, you know, this. All that matters is that this direction is perpendicular to the radius. Okay? Any other direction doesn't really matter. It could even be in a sphere, you know, it could be moving this way around the sphere. Okay? So if we set the initial velocity to this, right, this will mean that even though the only force acting on it is this, it will go in a circle. And we can do the same thing for F equals kx. If we say mv squared is kx, right, then we can say that kxr over m root is equal to v. If we set our v to that, then that's also going to be that's going to give us our initial velocity such that we don't fall in. So I'll just show you in Unity, right? So say we have something, right, and I've added a script to it called centrifuge, and it just pulls it into the middle, or any object. I've set it as this thing, right? So this thing's going to fall into the middle. We're not going to give it any velocity, we're just going to let it drop. Now, watch what happens. It gets pulled in, and then it shoots off. And you'll see it actually starts slowing down. But it's not going to slow down by much, because 1 over r squared, gravity's 1 over r squared, right? And 1 over r squared is very, very weak. It is decelerating very slightly, but it will never, it's escaped now. And the way we can tell it's escaped is we can look at it, we can calculate its escape velocity. Alright. So, say the escape velocity, right, means that you have enough kinetic energy to escape the potential of this gravity. So if you have more kinetic energy than this gravitational well has potential, then you'll escape. So you'll need half mv squared, right, to be equal to, I remember the work is integral of force times distance. So we got gmm over r squared, but we're going to end up, it's going to end up getting multiplied by r to, I think I've already taught you this, but that's the potential, right? It's got another r in it. Okay, so this thing is, we put these equal to each other. I don't really have time to fully go into that, but I think we did it before. That is your escape velocity. If you go above this, you escape, and you will never, you'll get out, as long as you're going straight up. If you move straight up at this velocity from the Earth, you will get out of the Earth's gravitational field, and you'll fly off into space, and you'll never come back. And presumably, looking at this guy who's now disappeared, okay, well, he's not disappeared, but looking at this guy, he's probably escaped, right? He got too close to the center and he overshot. This would never actually happen in real life. This happened because of the Euler-Chroma method, right? If we watch the steps, missed my timing. Okay, if you watch this, here there's this step where he's right next to it and he's expecting to jump 1 over it, and now that's the thing that's going to make him shoot. We can get it even more ridiculous here. I've got one called Wii, where this one happens to get way too close to center. Right, watch this. It happens to just pass it on that frame, and so that, you know, it's shot off to infinity, right? It almost divided by 0, right? Because it's 1 over r squared. So if it's 0.00001 squared, you're gonna go flying off. So in reality, you can never really get this close, because you'll bump into it. But anyway, ignoring that, let's now give it a velocity, right? And now this won't happen. Well, we'll give it 2, and it'll move around in a circle now. Well, it won't move around in a circle. It's going to orbit round. So there's only one force acting upon this, and that's the green force, right? It's gravity. You can see here I've set the type, force type gravity. So if we look, if it's gravity, we do some constant. I'm not doing g times m because g is times 10 to the minus 11. So if we're using floats and they only have 8 decimal places, then we don't want to be working with numbers that are times 10 to the minus 11. And when you multiply by the mass of the Earth, which is 10 to the 24, the whole thing's going away anyway, right? So I just use the sensible. I just call it constant, right? I just use the sensible constant, and I also use this grav factor times 100. I just multiplied it by some arbitrary value because it's going to make the numbers we're working with nicer. You know, we only have to type in a constant of 1 instead of 10 million, right? So we're doing, this is basically GMM over r squared, right, in the direction of the radius minus, so backwards into the middle, right? Because if we didn't do that, it would push it out. Okay, so I've drawn the line, and that's the only force acting on it. There's no other force. The only reason it keeps moving round is because nothing's stopping it from moving moving around, right? Which we'll come to find is conservation of angular momentum, right? When we talk about angular momentum, which we will today, if we have time. So let's talk about, okay, and if we had this as a rope, I also programmed a rope, so you can see this is, you know, F is kx, right? So that's just the constant k times the distance. So you see this one is, again, it's a 2D harmonic oscillator, right? There's one harmonic oscillator that's going up into the middle, right into the middle, up, and then you can see that the other harmonic oscillator is going out into the middle, out into the middle, right? So it's 2 sine waves that are 90 degrees apart, right? And then I made another one, which is just called centrifugal, which regardless of what I give it, will make it be in a circle. Because it's going to be, oh no. Oh yeah, because I overrid the y, so it won't actually. It's not going to work. You need to use this override. So now what I'm going to do is, I'm going to override the velocity with the velocity it needs to be in a circle. So watch this. Right? So this is moving in a circle, right? Let's do the rope. You can imagine this would be like a rod that's rotating. So it's fixed to some kind of rod. Okay. Now let's do gravity. Right. So all of them are rotating in circles, even though they're using these different methods. This one is directly doing mv squared over r. So we got mv squared over r, right? And I stuck it in the right direction using a cross product. We'll talk about that in a moment, but obviously it needs to go round. If you see here, when I override, so which I'm doing now, is setting the initial velocity. So there's no tricks going on, right? The only difference between this gravity where it's orbiting, right, and it's elliptically and it's falling into the center and then going out, the only difference between that and this is the initial velocity. There's no other difference. The thing that's keeping this from going in a circle is that it's falling sideways and then being pulled in. So it's constantly accelerating inwards, but because all its velocity is in this direction, tangentially, then it never gets to the middle. So you can see we gave it the right velocity here. So I gave it GMM over R, because if you look at this calculation, not that one, this, square root GM over R, square root GM over R. Okay? And then this one, this is if it's gravity, this one is if it's a spring or a rope. So this one is, remember we had root kxr over m. You can see we got k times, this is the x. Why is it the square magnitude and not magnitude? Over m. Oh, because we've got x and r. Right, so x is the distance, so that's actually r squared. Right, that's the same thing. Because we're the, you know, x is the radius here. X and the distance are the same thing, right? So that's the benefit of it, right? That's what centripetal force is. It's just any force that's pulling you towards the center of a circle, but then the thing that's keeping this going round forever is that it already has the velocity it needs to stay in. So when you swing a rope and swing a bucket around you, yeah, you need that initial torque to keep the thing going out, right? You need to add a torque to it to give it angular velocity. But then once it's spinning, you can just spin round with it, right? Like you're no longer having to add this torque because it already has that. You just have to pull it in. So once you take a bucket and you spin it round, then once you start turning round, all you're doing is pulling the rope back and the bucket's still going round. You no longer have to like add a torque, and we'll talk about torque now. All right. So that's just little demonstration. You know, this is probably going to take 2 lectures. No. Right. We're going to talk about angular momentum because we were just talking about this, right? So this is a conserved quantity. We've mentioned this before, actually. Okay. Imagine we have our solar system. Okay. Let's say a ball. A ball is made up of lots of tiny particles, right? Let's say it's a golf ball. Or let's say we have our solar system, right? And it's made up of lots of little things, right? Everywhere. And we can talk about how this whole thing has some mass, right? Some entire mass of the whole thing. And we can sum all of the momentums of each tiny little bit. We can add them all up, and then we can make that some total momentum, and we can talk about the momentum of the whole system and the mass of the whole system, right? And the energy of the whole system. And we can see correctly how it moves. Like, you can imagine that our galaxy is just one giant ball, right? And you can see how the ball moves. And then you can look at another ball like Andromeda, and you can see how the balls touch each other, right? But that doesn't tell you anything about the interior of these two systems. And the same thing about if you have a ball, and this has got water inside it, you know? Right? You've got 2 balls full of water. Well, how does the water move inside the ball? Okay? So, if we look, say we have a solar system, right? And we're interested, we know how this solar system moves in its entirety. And we know how this nearby, I don't know, Alpha Centauri or something? Is that real solar system? I know nothing about astronomy, by the way. I slept through astronomy. I did not care at all. Right, because we're never going there, so who cares, right? I care about, like, Mars, but I don't care about, like Proxima Centauri or whatever. But yeah, there's some, maybe that's a galaxy, maybe that's a solar system. There must be a solar system near us, right? And, well, not near us, but, like, somewhere, the nearest one to us. And we can see how these move relative to each other. But to see actually what happens within it, we're interested in rotations typically, right? So, I mean, we can talk about how these things, you know, there might be a comet that's going in and one that's going out, and those do affect how the whole thing moves. But really, especially if something goes out of it, right? But really, in general, most stable things, we're only interested in their rotation. Because, say, for instance, you have, like, a tennis racket, okay? Well, this thing, these particles aren't moving away from each other. They're fixed in place. But what we can tell is if I throw a tennis racket at you, you know, maybe it's going to spin round so it's that way. Maybe it's going to spin round so it's that way. Like, or maybe it's going to spin in this axis, right? So now, you know, so there's loads of ways this can spin. And so if we're interested in seeing what's going on inside a system, then we're less concerned about, you know, how this whole system is moving and how the momentum is. And we need to care about the rotations of everything inside it. So we can now define a new thing. So let's say we have our axis, right? And we have some right. Say this thing is a particle, right? And it has a radius away from us, r, and it has some momentum, p. So it's flying this way, right? You can see, for instance, if this was a planet, it would be going around us, right? If there was a central force pulling it in, then it would, or if it wasn't such a strong central force, maybe it would do some kind of orbit like this, right? But we can see that this thing has some kind of angular momentum, right? Whereas this thing going directly up has no angular momentum because it's not turning, right? It's just moving outwards from us. As long as it's nothing's changing in here, right, there's no angular momentum. So we're going to say that our angular momentum is equal to our normal momentum, well, our distance, right, crossed with our linear momentum. Okay? And in this case, we've actually got quite an easy, right, crosses will go in and out of the page, right? I can't draw a cross, but I can show you how long it is here because I've used a very special example where this is at 90 degrees. If you just want to calculate the magnitude, you can use this formula is RP sine theta. And this is actually a really convenient one because this is theta. In this example here, we have pi minus theta, right? Well, if you look at a sine wave, if that's sine theta, right? And that's minus sine theta. Oh, that's sine minus theta, right? It's mirrored, you know, we're flipping it. So we're flipping this side to here. Right? If we then add on pi, sine pi minus theta, so we're pushing it that much, right? You'll see that it actually pushes to here. So it's essentially, right, so we've got, this is sine minus theta, right? We're pulling this back 90 degrees, 180 degrees, whatever. And you'll see we just get sine. It's the same thing. You can look this up yourself. Sine theta equals sine pi minus theta. So the sine of this is actually equal to the sine of this. So in this example, if we've got a triangle, you know, SOHCAHTOA, I don't know if this is how, well, you must have a different name for it in Austria, but we call it SOHCAHTOA. We call it, in this case, it's SO. You'll have done this in high school. Maybe you didn't know how to do it by this name. This is the hypotenuse. So this is sine this over this. Right. O over H is sine of this angle. Right, so H sine that is... Wait, this is the hypotenuse. This is the opposite. So H sine that is that. So it turns out that this, right, is the if you multiply this vector by this vector, just the magnitudes, then you'll end up with the cross product. But that's a very specific example, right? In reality, you're going to be looking at things moving in and out of the page. So I flicker past that because it's not really important. I only did it because my dynamics textbook teaches that I'm going through, and I just think it's a stupid example, to be honest. So I don't know even why I taught it to you, but there you go. The reason it's a stupid example is because if I just move this vector slightly, right? If I move it that direction, or say the momentum's going up, right? And now, if this momentum's going up and I try and take 90 degrees, it's not going to give us any, it's not going to connect with the origin. So it's a stupid example. I don't know why they even wrote that, but I'm going to show you how it actually works, right? We've got our particle. It has some momentum. Then what happens is we take the cross product, which means we're either going backwards or forwards, right? If we have one angle going this way and one angle going this way, the only thing that can possibly be perpendicular to that and that is where my head's going now, right? That. Right? So this thing, we know it's either going that way or that way. Right? And the whole thing depends on how we define our coordinate system. So, how familiar are you all with determinants, matrices? Are you all good on matrices? Do you know what? We're just doing. This is gonna span 2 lessons anyway, so let's just do a quick cross products lesson, right? L is r dot p, r cross p. How we calculate that is, we have this matrix. It has our directions at the top. Right, and then it has our r values of x, y, and z here, and then our p values of x, y, and z here. Okay, and then we can find the determinant of this matrix. The determinant means we chunk it into 3 little mini matrices, right? We grab this and chunk this matrix out and multiply them like this. So right, times the det. So how that works is, it's d minus d. Okay, so that minus that. Okay, so it comes out, you should have been taught this, right? ry pz minus rz py, right? Then you move on to your j, okay? And you yank this matrix out, so this makes a new matrix. So you can imagine we had one like this. It's this half, slot it onto this half. Right, this is just one big matrix. And we do that one. So, and for some mystical reason, this goes negative. Right, so that's minus j rx pz minus rz px, and then plus k, we take our k, we grab this as a matrix, so now we're going d, so we've got ry px, sorry, rx py, rx py, wow. Come on, pen, what's going on? It's like a biro sometimes, it just runs out of ink, right? So rxpy minus rypx. Voila, you now have a cross product. Right, so that's how you calculate a cross product. You shove it in this giant thing, right? That's how you calculate the angular momentum, right? Where these are your directions, and this is this. So we'll do an example. We'll stick, we'll go, let's say here we have something that's at 0, 2, and it's moving right up as 0, 3. Okay? So we're going to calculate its angular momentum from here, from the origin. Okay, well from the origin, we've got ijk, we've got we're doing it in 3 dimensions, so let's do that. We've got its position, which is 020. We've got its momentum, which is 030. Okay. So if we find the det of this, we can see that if you hold I, you're going to multiply these together. So these are both going to get multiplied by 0. So that's going to be 0, right? Then you're going to have j, and that's just 0, 0, 0, 0, so that's 0. And then you're going to have k, which is going to be 0 times that times 0 times that, so that's 0, right? So whatever happens, this thing is just giving you a 0 angular momentum, because all of it is in one column, right? As long as all of it is focused in one column, you've got no angular momentum. Okay? So now what if we instead say, well, we're going to look from here. We're going to move right, so now we're at 2, 0, 0, and we're going to check the angular momentum of this particle from here. Right? Well, now, if we look at this, we've got ijk. In x, relative to this, right, y is still 2, okay? But now x is minus 2, right? Do you see? We've got to go minus 2 to get to here. So x is minus 2, z is still 0, and the momentum's the same, right? It doesn't matter where we are, the momentum is constant, right? It's going to be that. So this is 3, kilogram meters per second. We'll say that it's got a mass of 1, so it's moving at 3 meters per second up, right? So now if we do the cross product of this, if we look at this, right, we got I, and these are going to be 0 again, 0, 0. So that gives us nothing. We've got J, and again, 0 is those ones, 0, 0, nothing. But now we have K, okay, minus 6 here, 0. Okay? So you can see we've got minus 6K, and that's going to be our angular momentum. Right? So it's minus 6 in the K direction. Two things to note here. One thing, let's, instead of calling them this, let's give them more generic names. So we'll call it Rx, Ry, Rz, Px, Py, Pz, and in this case, these ones are equal to 0. Right. Well, we can see here that this gives us Rx, Py, K minus. Well, yeah, it's just, in this case, it's not a minus, but, right. So, the important thing to mention here, okay, and remember, K is 110, so it's essentially, this thing is the same as minus 006, or, it's 00 minus 6. This thing is the same as 00 RXPY. So the point is out of the page, right? The angular momentum, this one has no angular momentum because it's only moving up, right? As long as it's only moving away from it in terms of distance and not angling around it, if there's no angle change, right, then there's no angular momentum. When this moves back, the angle doesn't change. But looking at this as our center, right? Well, if this moves up, its angle changes. Look. There's a new angle, so it has angular momentum. So you can have angular momentum in one frame and not have it in another. It's not some constant thing that's the same in all frames. In some frames you do not have any angular momentum at all, right? So another important thing is we have to know where is RK. Okay, because we know that Ri is that way, right? And we know that Rj is this way. Now, typically, when they teach physics, they teach K is this way. But when we use unity, that's absolutely not true. K is this way. Okay. So you might be like, whoa, well then, if K can flip, right? If we have some IJK times, Rx, Ry, Rz, and this is the det, Px, Py, Pz. If K can just change if K can be the opposite direction, then what does that mean? Because how is that going to change everything? Right? Won't that flip the angular velocity? Well, let's give an example. All right. Unity's left-handed, right? Z is forward. It's called a left right-handed engine, and I'll explain why in a moment. But if we imagine that we have going up some particle, right, and it's got a momentum that goes left, right, and it's got some r, right. If we do this, we got 0 ry, you know, it's only got a y. 0, we'll call this minus px because it's, you know, an x in the negative direction. 0, 0. Right? RL, our angular momentum, is going to be, again, it's just going to be k, because these ones are going to have the zeros. Right, so it's going to be k, 0, 0, minus r rypx. Okay. Or actually, we'll not call it minus. We'll just call it plus. Whatever. We'll just call it positive. Okay. Rypx is going to be multiplied by 0, 0, 1, right? And that's going to be our angular momentum. Well, in this case, L is anti-clockwise, right? We can see that this has given us a positive, and do you see it's positive? Right? We're getting, actually maybe we should have done the minus. Minus Oh yeah, we do want it minus. Okay. Yeah. Okay, sorry. So remember, if you've got A, B, C, D, you end up with AD minus BC. So in this case, we've got AD, which is 0, 0, minus RYPX. Okay. And this is already minus, so that ends up positive. So we end up with a positive value for angular momentum, even though this is going backwards, see, right? So we've got a negative value, right? And it's giving us, I know that that's actually opposite. We could call that, we could say P is that way, right? But when we have a negative value, we're getting a positive angular momentum is the point. If this is minus 3, right, then we're getting a positive angular momentum. And that is the important thing about that is it depends on your coordinate system entirely, because if we go in Unity and look at this thing, right, I've given it an angular momentum. Or I just gave it an angular velocity immediately. See how it's spinning left, right? It's going to spin left. Let's imagine we were in a right-handed engine. Okay. Right, so here's our thing. Right, it's spinning left. If we were in a right-handed game engine, we would be this way around, and it's now spinning right. It's the same thing, right? It's just depending on where you're looking, and the angular momentum's the same. It's still got the same value of angular momentum. It's just which way you tell angular momentum to resolve. So like the angular momentum of this and the angular momentum of this is identical, right? It's the same thing. It doesn't matter what side of this we're on, the angular momentum's the same, but the way it spins is entirely down to your coordinate system. And it happens that in Unity, we use left hand, which means, right, let's say we have some thing, right, we have some particle, and it's moving left. So we know, because it's rotating, right, even if it's not rotating, even if it's just moving in a straight line, right, it's got angular momentum because its angle is changing. Its angle is going to be decelerating as time goes on, because eventually, you know, it's only going to move from here to here, which is not much of an angular change, right? Whereas at the beginning, when it moves, it's going from here to here, which is quite a big angle compared to this, right? it would help if I drew straight lines, but whatever. As it approaches, you know, if it goes in a straight line, eventually it's going to approach 90 degrees, but very, very slowly. Whereas in the beginning, it makes quite a bit of... It changes angle quite fast, and then the angular change slows down if it's just moving in a straight line. Right. But let's say this thing has angular momentum. Right. We can say that, okay, you put your hand up in the direction it's going. So I'm going to imagine I'm you. Don't think about it from my perspective. Think about it from your perspective, because obviously in terms of that Unity example, right? You're here behind the thing. I'm here on the other side of it. So just think of this from your perspective and not my perspective, because we have completely different worlds right now. Like I'm gonna talk about your left-hand world. That's the same as my right-hand world. Okay, so let's say this. Can I also get this down? Right. Let's say this. Right. The vector's going up, right? In this example that you can see here, there's a vector going up. That is x for you, right? Assuming that that's positive x, right? Someone tell me that I'm right and it's not flipped for you. Is this like x positive for you? Yeah? Someone? Okay, good. That's y positive for you. Okay? For you, in Unity, this is z positive. Towards me, I'm in your positive z. Okay? Now, we put our hand up, right? And you can see that it's bending that way, right? For you. For me, it's bending that way, right? But for you, it's bending this way. So you've this thing I've drawn here. Wait, this is up, and it's bending this way, right? So I put my hand up, and I'm bending my fingers in the direction that it's bending, right? So with your left hand, because we're in a left-handed system, you'll see that if it's going up and it's bending that way, then your thumb, if you stick your thumb out, right, your thumb will point in the direction of the angular momentum. So in this case, the thumb's pointing towards me, right, which means that the angular momentum is going in this direction. So if you have a positive angular momentum in Unity, because it's a left-handed system, that means that as you apply an angular momentum forward, a positive one, which you would when we were using 2D, for instance, angular velocity is just in Unity 2D. If you do r dot angular velocity equals 3, that's the same thing as 0, 0, 3 in Unity. Okay, for 2D. In 3D, you can't do that. You need a vector 3. Okay, but so if you're applying a positive angular velocity, right? So you've got your hand up and the thumb's coming out towards me. That means it's bending left, right? Whereas if it was negative, my hand would have to bend that way, right? So if you see it moving this way, if you see this bending in this direction, right? You see the particle going right, then that means that the angular velocity is negative. So we can see here, let's give a negative angular velocity in z. So that's the same as 0, 0 minus 5. Okay. Now it's going clockwise, because you've got, you know, I'll move to the same plane of reality as you guys for a moment. Right, this, we're turning right. Right, we're going up and then turning right, so the angular velocity is backwards. Backwards is negative. So that's how you should think about angular velocity. We got through about half of the cards, because actually this topic's much more complicated than I thought I could batch it out in a lesson, but we really can't. So you're a bit confused. Well, it's okay to be a bit confused, because we're going to drill it in again tomorrow. But yeah, I hope you at least got that bit. The main thing is you should be able to. It's important to know about cross products, right? Like what they actually mean. Like a dot product. In case when I was first taught dot products, I was like, "What are you talking about? Like, this is like, okay, A B cos theta. What does this even mean? What's the point of this, right?" In terms of game engine, what's the point of a dot product? Well, the point of a dot product is if I'm like here, I'm here, and I want to find out what proportion of my velocity is heading in this direction. Then if I dot this with this normalized vector, I find out what chunk of it is in that direction. So dot products help you look at things and go, oh, I have a velocity this way. How much of it is horizontal? Well, I'll dot it with the horizontal, and then that will give me, I'll dot it with 1, 0, 0, and that will give me my velocity, like my horizontal velocity. Or if I dot it with the vertical, I can find it in this direction, right? So that's your dot product. Your dot product will, if you land on the ground, if you land on something and you're like, okay, am I on the ground or not? And you don't know that the gravity in this game changes, right? So maybe your character's pointing this way, right? Gravity's down in this, instead of normally gravity's right down, but what if your character, for whatever reason, is pointed up like this, and you want to find out if he's on his feet? Well, if you dot his down with whatever you hit, right, the normal of that, because the normal of whatever you touch will always be pointed up. So if you dot the normal with him, they'll be in the opposite direction. So if you dot the minus the normal with him, then you'll find what percent of it is going in the direction of the thing you're hitting, right? So that's what dot products are useful for. They're useful for checking angles of things, right? Cross products are useful for finding, hey, I got this one and this one, but I want this one, right? And you can see that I actually did it here. I used cross products here, okay, when I got I wanted the force. Okay, if I go back, I wanted my GMM over R squared, right? I wanted my V. The V needed to be in the direction of theta, right? And I don't know what that direction is. If I'm sitting in my game engine and I can tell you, okay, I have some mass here, I have something moving down towards it, right? But I don't know the perpendicular vector. Well, I mean, you could actually do some probably basic maths to figure that out. But, I want this vector, and I know this, I know this. Right, that's one vector, by the way. It's just a terrible drawing. I know this vector. I want this vector. But I also know what way forward is. Well, if I cross that and forward, I'm gonna get this, right? If I take that and cross it with forward, or maybe backwards, well, we can check, right? If we take our initial vector, so it's going up and right? So, we're trying to find we got here's our player, and we know that's our object P, that's our origin. P minus O gives us this vector, right, R. So, R is in this direction. If we do R, and we cross it with forward, right, so we cross it in Z positive, right? This is, I can't draw out of the page because I can't draw in 3D, but imagine that this is into the page, right? So we're going like, maybe if I was a better artist, I could draw it. This is an arrow going into the page, right? If I cross this R with forward, I'm gonna go, R is that way, then forward is curling that way, right? So in a left-hand coordinate system, that means, all right, so I should probably do it in how you see it. You see it like this, right? R is that way. Okay. To you, R is that way, okay, and then P is, you're now, we're gonna cross it with forward. If we cross it with forward like that, right, so we've got R's that way, we're crossing it forward, then we can see that this way is going to give us that, down and right. So if we do R cross vector 3 dot forward, then we'll just get the minus theta direction. And if we do R cross with back, vector dot back, right, then we'll get theta in this direction. So that's what I did. If you look here, I said if you're clockwise, I cross it with forward, otherwise I cross it with back. Okay? And then if you know, if we look at these, I'm gonna move it clockwise. You know, then it's just crossed in the other direction, and that's how it knows which direction to go in. I calculated the magnitude, but the only way it knows its own direction is I took the radius, right, this green line, and I crossed it with forward, and that gives me the perpendicular vector. So the joy of cross products is, often in game engines you want the other direction, right? You're like, well, I know this way and I know this way, but I want forward, or I know this way and I want this way. And when you're rotating things, that's what you want, because when I rotate my phone, you know, I know if I'm connecting my phone to my arm, right, I know where it is, and I know where it's rotating. It's rotating that way. So which way is the angular velocity going to be? It's going to be the axis. It's going to be my arm. The thing that's rotating this is my upper arm, right? And it's and my arm is rotating in Z, right? This actual pivot, the thing that's causing the rotation and applying the torque is my upper arm, and my upper arm is only spinning in the Z direction, and that is causing this arm to move in both X and Y. Okay, so we've got this R, this is the R. In fact, you don't even need the pen, right? Well, I mean, it helps to think that this is what, well, if I hold it this way, right? This is its momentum, right? It's going up, right? Then when I rotate this, when I apply a torque in the Z, when I apply this, when this thing rotates, this Z thing rotates, I get momentum in Y, in this case, in X. So I cross this with this, I get this, right? I hope that's clear enough, because I've shown it how it works mathematically. I've tried to explain it, but you can also do the Fleming's left-hand rule, right? You got instead of doing it like that, you can do it like that, and that's right hand. Now in physics, normally they use right hand because they say, oh, Z is that way, but it doesn't matter, right? A positive, even if you set your angular momentum as negative, like you set your k direction as the opposite way around, the angular momentum is still going to be the same value. It's just going to be when your engine applies it, it's going to be turning it in a different direction. So when your engine goes, okay, time to turn this because we have an angular momentum, it's going to say, okay, well, it turns around k, and k is either that way or k is that way. I don't think I can explain it better than that. That's my best attempt to explain to you cross products, which you need to know to understand rotation. I think the arm thing works, right? I think you should sit there and actually do that yourself. Look at your arm, bend it 90 degrees, right? You got to have it out and then bend it 90 degrees and rotate it and convince yourself that, yeah, the only thing that's rotating is this, you know, the pivot, which is in Z, which is your upper arm only goes forward and backwards. It's going from the back shoulder to forwards, Z, right? And this this is your R, and the direction that your hand ends up going, the angular change, is, you know, that thing, right? This cross with this gives you this. They're always, this cross with this gives you this. This cross with this gives you this. Maybe not in the right direction, but in general, when you cross this and this, you get this. When you cross this and this, you get this. I don't know which way around, but you can figure it out, right? So cross products give you these. This is my gang sign. It's the cross products, right? Anyway, that's it. That's the prep you need for next lesson. So let's say you have. Oh, you know what? I can't even draw on them. Okay, you have some cube, right? And the origin can be anywhere, right? But let's say we're looking at the center of the system, right? So you can imagine that that's actually halfway through there, halfway up there, and halfway across there, right? Okay, so I guess the center's more like that, right? So we've gone, we've gone X, Y, and well, no, Z, Y, X. Okay, and now we're at the center. Well, every single point on here, you can say if the cube starts moving relative to this point, right? So the cube moves up. Well, say we talk about this corner. This corner is changing angle, right? Because as this corner moves up, so if we imagine it ends up here, okay, then it will now be here, and that's an angular change. Okay, so this thing has some angular momentum. However, this one here directly up, right, has no angular momentum because it's not changing angles. So if this whole cube moves up, right, then you can, and you have your origin in the middle of the cube, then you can cut out a slice here, and you can say, well, this entire cylinder here, right, this little infinitely thin cylinder of your cube has no angular momentum. But the further you go out, the more angular momentum it has. So once you get to the edge of your cube, the very corner, right, this one up here, this one has a lot of angular momentum in comparison to this. So as this moves up, this is the one that's changing angle most out of everything, right? So yeah, you can look inside your system and say, well, this system's made of loads of teeny tiny points, and every one of them has their own angular momentum. And that's, even though we can just look at this entire cube and say, well, this has a momentum of P, right? We can look in the inside of it, and all these individual ones have their own little P's, but more importantly, they have their own little L's, which will be their R crossed with their P. Right, so it'll be the R, we draw it to that point with that P, which happens to be the same for all of them, right? If they all have the same, if the whole cube's moving at 1, then the P is going to be the same for all of them. But the difference is the R is going to be different for all of them, right? So every single one has their own little R. And we're talking, don't worry about this because we're going to talk about it more next time.